Hello my YouTube friends, we continue looking at the examples of Laplace transforms in electrical circuits. So now we look at example 1, and in this example the question has been asked to find V naught at t assuming zero initial conditions. So what you have here is the voltage source, which is U at t, which is a unit value. We've got 1 ohm, 5 ohm, 1/3 farads, an inductor of 1 Henry, and there's a voltage across that inductor, which is V0 naught, which we've been asked to find using the Laplace transform. Now, what you get here is that, first of all, this is the time domain. We have to convert the circuit to the S domain. And to convert this to the S domain, what you will know is that U at t is simply equal to 1/S, and then our 1 Henry inductor is going to be equal to SL, and we know that L is 1, so we simply multiply S multiplied by 1. It gives us simply S. And then later on we look at the capacitor, which is 1/3 farads, and this is supposed to give us 1/SC when you convert it, and this simply ends up being 3/S. And these are the values that we've replaced. So across the capacitor, you've seen the value is 3/S. The voltage source is simply a unit, 1/S. And then you've got the inductor here, which is simply S, as we have found S multiplied by 1. And so we can adopt any preferred method here, and I would basically use the mesh current method. So create mesh currents there, mesh 1 and mesh 2. So this is going to be the mesh current I1S, and this is going to be the mesh current I2S. And therefore, to get the solution, we start with mesh 1. So to get the solution for mesh 1, what we have in mesh 1 is we've got the potential, which is the voltage source here, 1/S, should be equal to the voltage drop plus the voltage drop across the capacitor and the voltage drop across the the resistor. And then we've got a shared current, which is a current I2 on this capacitor. So what we have here is 1/S is equal to 1/S is a positive because the current moves out of the positive terminal, and here we have the voltage drop across the resistor plus the voltage drop across here. So we'll take this simply as 1 plus 3/S. This multiplies by I1, which is this current here, I1S, and this subtracts the current that is flowing in the opposite direction from I2. This current is multiplied by the voltage drop across by the value of the capacitor here. In this case, we've got 3/S. This multiplies by I2. So this is mesh 1. And then we go to mesh 2. In mesh 2, we don't have a voltage source. This implies that the source value is 0. And what remains is that we've got the I2 multiplied by the voltage drop according to KVL, I2 multiplied by 5 ohms, and then we've got I1, which is in the opposite, is going to be a minus, so we can say minus 3 over S multiplied by I1, and then the rest are all positives. We've got the S, we've got the 5, and we've got the 3 over S. That multiplies by our I2. So what we get here is S plus 5 plus 3 over S, and that multiplies by I2, and that is our second mesh. And thereafter we could simplify this equation by taking I1. We can say I1 is equal to 1 over 3, and this multiplied by S squared plus 5S plus 3 I2. And we can consider this as equation 3. Then we take equation 3 now and replace it into equation 1. So in place of I1, which is this I1, we take this O variable and put it in that equation, and we solve further. So what we get? What we get when we replace this equation, so we take this equation and then insert it into that equation, the first equation. So what we get is so we are saying we are replacing 3 into 1, and what we get here is that we've got 1 over S. This is equal to, we've got 1 plus 3 over S, this is 1, and this multiplies by 1 over 3 multiplied by S squared. We had S squared plus 5S plus, as we had, 3, and that multiplies by I2 minus 3 over S multiplied by another I2. This is what we get. And then we can simplify this by multiplying everything by 3S. We multiply everything by 3S, and this gives us 3 equal to, so the S cancels out, we remain with 3 equal to S squared plus 8S, sorry, this is going to be S cubed plus 8S plus 18S, and this multiplies by I2, and we could therefore say I2 is simply equal to 3 over S cubed plus 8S plus 18S. Okay, so that is our I2, and we know from here that our I2 is in the second mesh, and therefore when we come here we should also know that the voltage across the inductor VOS is going to be equal to S, which is the value. If you remember, this is the S. It multiplies by the current I2, which is in this case I2, and this simply gives us we've got 3 over, we've got S squared, now it's squared, plus 8S plus 18. Yes, there must be a square there. So what we get now is this variable, which we now have to simplify to get our solution. So what we get here is 3 over square root of 2, and this multiplies by the square root of 2 over S plus 4 squared plus square root of 2 squared. From this we take the inverse. So you can look up the tables, simply look up the tables, and we can find the solution when we take the inverse to be equal to 3 over square root of 2 e minus 4t sine square root of 2t volts, and that is for time t is greater or equal to 0. So that is example 1. Now let's look at example 2 of the Laplace transforms in electrical circuits. So when we come to example 2, the question says you have a voltage source that is of value 10 E minus T unit, or U at T volts, and then you've got 10 ohms resistors each, and then you've got the voltage VO V naught at T, which we've been asked to find, and the capacitor value is 0.1 farads. And then we've got the current value here, the current source value, which is 2 delta T amps. And we've been asked to find V naught at T, which is this one. And we assume that, so we're taking an assumption that the initial voltage value is 5 volts. So the capacitor is charged at this to 5 volts. And then let's see what happens. So the next step to do is transform the circuit into a Laplace transform circuit, so into the S domain. So we've got this is a T domain circuit, and we transform it into an S domain circuit. And in the S domain circuit, what we are going to have is we've got 1 over S here, so it's that simply becomes 10 S plus 1, and then we have 10 ohms staying the same. Across the capacitor here, we've got 10 over S when we convert that, and then we have so we chose to convert the capacitor into a capacitor parallel to a current source, and the current source value is calculated from CV naught from the initial conditions, and this it gives us 0.1 multiplied by 5, and it simply gives us 0.5 amps. Okay, and this is the 0.5 amps that we get here. And then we come to the current source value here, which is simply 2 amps. So we get our 2 amps like so. And You can use any preferred method, but I would want to use, I'm seeing this as one node, so I want to use this as and take it as v null s. So this is one node, and I can apply node analysis by simply grounding, taking this other node as a reference node. So this becomes a reference node for me, and I ground it so it gains zero potential. And if I find the voltage V null S, then I've found the solution. So how do I get through this? What I have is I have a current flowing from the source in this direction, entering this node. Then I've got a current that is going to leave that node, another current leaving, and then I've got this current which is already in this direction, entering the node, and the current, another current entering the node. So we are saying, according to KCL, the sum of currents entering a node must be equal to the sum of currents leaving that same node. And accordingly, we've got this current, this is entering this node, which in this case, if you take an imaginary node here, which is going to have the value 10 over s plus 1, and that is going to have to subtract the voltage V0 over the resistance. So this is going to appear as follows. You have 10 over s plus 1, and that subtracts the voltage V0 over the resistance, which is 10 in this case. And this is the current, this value of current here. And this must be able to add to the currents that are entering. So sum of currents entering must add. So this adds to the sum of currents entering. In this case, we've got the 0.5 plus the 2 amp current must add. And this must be equal to the sum of currents leaving that same node. So in this case, what is leaving, we've got V0, which is V0 here, over the resistance, which is 10, plus the current that is leaving here, which is V0 over 10 over S. And that's the current flowing through the capacitor. And then we can simplify this further. So I'm gonna go to the next page. So if we simplify this further, we get 1 over S plus 1, and that is plus 2.5. This should be equal to 2 V naught over 10 plus S V naught over 10. And if we can simplify this further, we can get 1 over 10 V naught, which is S plus 2. That is, if we simplify that further. And then if we multiply everything now, all this, we multiply by 10, what we obtain is, now we cancel out the 10 on the other side. So what we remain with this side, we remain with 10 over, which is 10 from there, S plus 1. And this adds to 25. This 2.5 becomes 25. And this should be equal to, here we've got the 10 cancelling out. We've got V naught S plus 2 as as the final solution. Not the final solution, as what we get on the right side of the equation. So now we get, if we take V naught and make it the subject of the formula, then what we get is 25S plus 35. This divides by S plus 1, s plus 2 and this can be equated to a s plus 1 plus b s plus 2, and we must be able to find a and b in this case. So for us to be able to determine a, let me use the next page. To determine a will be equal to s plus 1, this multiplies by v naught s, and we're taking s to be equal to minus 1 so that we can cancel out s there, and this should be able to give us 25s plus 35. This is divided by s plus 2. We take s equal to minus 1, and if you look at this, we're going to obtain 10 over 1, which is simply 10. So a in this case is equal to 10. So we're saying a equal to 10. And then we get b in a similar way. So our b is equal to s plus 2 s plus 2 v naught s, that is when taking s equal to minus 2. This gives us 25s plus 35 over s plus 1, and we're saying s is minus 2, and this gives us minus 15 over minus 1, or in short we are saying b is simply equal to 15. So having found these values, therefore we're able to determine or write v naught s as equal to v naught s is now equal to 10 over s plus 1 plus 15 s plus 2, and then we take the inverse of this. Take the inverse, you can use the lookup tables, and you come up to get the solution to be of the form v naught at t to be equal to 10e minus t plus 15e minus 2t, and that multiplies by the unit volts, and this is how we arrive to the solution, and that is how we get the solution of example 2. So more examples can be found in the book on Alexander, and you can look up those examples. Thank you for watching. Subscribe to my channel, and we'll see you again soon.